Okay, everyone, welcome here today. Both of you are here actually on site, but also for you who are attending online, because as you know, we are also streaming at the moment. My name is Eleanor Devine. I'm head of office for research here at Sveri, which is the Sweden Research and Innovation Office here in Brussels. For those of you who are not familiar to Sveri, it's a joint office between the Swedish Research Council and Vinnova, which are the two of the largest public funders in Sweden for research and innovation. We are 3 people here based in Brussels. So with me here today, I have my colleagues. It's Anne-Marie Fineman over there and Isabella Ismail, both representing innovation and Vinnova. Okay. I thought I'd start with some practical information first. The first one is that, as you might have noticed, the Q&A has been moved to the end. And the reason for that is because we're going with the Chapman House rules, which means that the Q&A will be sort of closed sessions. They're not going to be streamed. They're not going to be recorded. So please keep your questions till the end of the seminar. It also means, unfortunately, that you who are participating online will not be able to ask questions or anything. But yeah, that's unfortunately how it is. Okay, so, but let's talk about the seminar now. So we are here in Brussels, at Sveri. I'm very happy to present this new initiative, the Nordic initiative, Polar Connect. For me, with my research background, I'm very fascinated by the research part of this new initiative. But I'm quite sure many of you perhaps have been sort of had other things that caught your attention with this initiative. For example, how we can improve digital transfer, boost business, or sort of even create a European digital sovereignty. So, and I completely understand that. But what we thought here is, of course, that with an initiative like this that can offer so much for so many here in Europe, it would be a great theme for a seminar, which is also why we decided to have this initiative to come here and present for you. But let me not take more of your time, but instead present our first speaker, which is Walter Nord, the director of Nordnet. Who I think can present this project, this initiative much better than I can. So over to you.
Thank you, Eleanor. So why are we here today? We have a fantastic project that we have been involved in and working on for a number of years. The Polar Connect ID came about quite some time ago, and it has been in some iterations going back and forth. And it looks like it's coming closer to a reality. And the research angle with the smart cable is something that we did not anticipate a couple of years ago. So there are some news in that perspective, and we'll get that one. So, there is formally there is a project that we have submitted that's called North Pole Fiber. That's good to be aware of, and that's the next step of Polar Connect. We'll get back to that one towards the end of my presentation. The goal of this here is to raise awareness of what we are doing, raise awareness of the possibilities of connectivity from Europe to Japan, Korea, to Asia, going over the Arctic region, which is a route that is currently unexplored. Some can say that this is an opportunity, some can say that this is a sad aspect, but the geopolitical aspects of this cable has never been more on the table as it has been over the last months or the last year. The sovereignty and the independence of having independent connections to Asia is as ever needed. Currently, the connections that we are seeing at the moment, they all go through the Suez Canal. They all go over Russia, or they go over United States, cross United States, and go over the Pacific to Asia. That's a very, very long way. When you have long ways of the subsea of the cable system, they get slower. They get less efficient. And multiple connections is the way for redundancy. How many here heard about Nord Stream? And the rest didn't. Excellent. There is no way to protect submarine cables. They are They're about this thick, about a thumb. And if you are intent on doing something to a cable, there is no economically feasible way to protect cable systems on a long-term basis. And the way to introduce protections is by redundancy, is having multiple paths. We have the Suez Canal, we have over Russia, we will have over the Arctic, there will be connections over the US. And that's the way the whole internet is being built, as a redundant system. And this is something that is adding to that redundant system. We got a little bit of an unexpected boost in interest in this. Not sure if you have seen the tweet, but Margarete was tweeting from the G7 meeting that is ongoing in Hiroshima in Japan about the importance of connectivity between Japan, Canada, United States, and Europe. So that is also a place where this discussion is taking place at the moment, the increased dependency that we have on our global partners. And both from a research perspective, but also from other perspectives, the connectivity enables so much more than it's just being a cable. It enables the exchange of information between HPC data centers in the northern part of Europe, with Japan, with Korea, with the whole region. It enables direct connectivity. That there are going to be new opportunities that we don't envision today when we open up a high capacity cable like this one with a direct connection from Europe to Asia. If we look at the, just out of the blue, there are about 400 submarine cable systems in the world. Roughly, give or take, 400. So it's not like there are tens of thousands of cable systems. It's about 400. And this will be another 2 systems that will be complementing the existing 200s. And submarine cable systems are in, if you would say, short supply. There is a lot of need for more capacity. There's a need for more cable system, and there's a need for that increased redundancy. This is also part of what we believe to be driving or pushing the EU global data gateways concept. The northern connectivity of Europe will give us a direct connectivity to Asia over this one. And a couple of years ago, who would have thought that you could, if you could go, and just put a cable under the Arctic. But we'll hear more about the icebreaker and the possibilities about this one in the upcoming presentation. But it is feasible. We are seeing, and the studies that we are involved in at the moment are showing that this is a possible project. It's difficult, yes, but it's definitely doable. There will also be a presentation, Copenhagen Economics, about green data centers. If you would say, the advantages of having data centers close to where you have efficient cooling, where you have stable, environmental friendly electricity energy. And if you make the comparison of the cost of building a high power cable system from the north of Europe to south of Europe versus building connectivity between north and south of Europe, we'll hear more about that, but that's a tremendous advantage on having the data centers where you have access to free cooling, to good connectivity, which is the same if you look on the other side of the sea in Japan, where they have the same challenge. Another one, and this is the smart cables that I mentioned a little bit earlier. Climate. Sea level is rising. There is a possibility now so a subsea cable, the laser that shoots the information goes there, and then after some time it needs to be repeated because the signal drops. And at every time then you put something that's called a repeater, and in that repeater nowadays you can connect things. You can connect sensors that can measure temperature. You can measure salinity, the level of salt in the seawater. There are a lot of things that you can measure. This is a field that is opening up, and we'll hear more about that. It's tremendously important for the research aspect and for the researchers to getting access to real-time data. There are challenges in this field when it comes to, if you would say, the military aspects of this, but the other use cases of the monitoring perspective of the cable is tremendous. You will know more or less how the cable is doing, if it's being moved, if it's being touched. It's amazing. We'll hear more about that one. And it is being asked for by the research community to have access to this kind of real-time information, which hasn't been given before. So our vision, we call our vision Polar Connect Vision 2030. By 2030, we hope to have established 2 cable systems. One called Polar Connect, which is the green one, that is dependent on some icebreakers, and the yellow one, which is also dependent on different icebreakers, that is far north fiber that is being constructed or being looked at to be built over the next years. Both cables face challenges. The yellow one, much longer. It could be argued that that one has harder ice to go through, while the green one is more direct, has a shorter path. Can be argued that it's simpler ice to go through. Again, I'm not an ice expert, so I'll leave that for others to discuss. Our current starting point in this one, our next step in Polar Connect, is to look at the connectivity to Svalbard. So that's the first stepping stone, where we look at this blue connectivity going to Svalbard. Securing access to Svalbard will give us the stepping stone to go from Svalbard to Japan, to Korea, to Asia. This is still an application that has been under review and has been sent in and is pending the outcome of the discussions with the Norwegian authorities. So it's uncertainties in this project still, but we are hopeful. With that, I think that I have about 30 seconds to go, and I say thank you very much.
Thank you, and also would like to give you a small present for coming here today. So, and then I would like to present our next speaker. It's Dr. Bruno Basilescu, who's a director at Copenhagen Economics. He works as a consultant too, focusing on economics and policy and impact assessments. And he will here today present economic value of submarine cables in the Arctic. So welcome, Dr.
Yes, please don't leave me without slides. A consultant without slides is like a naked human being walking in the park. Thank you all for being here today. Thanks for the introduction, Walter. It's an exciting seminar to be part of. And we appreciate the opportunity to contribute by our research on behalf of Nordic. And this is not a new research question for us. We have worked on this topic in a variety of contexts in the private sector, also thinking about more broadly, what do infrastructures do for society? What are the socioeconomic impacts? What is the value? And how to go about understanding, first of all, the channels of impact, the conditions by which infrastructure supports the economy, and then the quantification of benefits. We know, and that is clear, that demand for data traffic is going up and up. This includes also, and not only, the data traffic that research and education activities, if you were to consider it as it is a sector of the economy, an industry, so to speak, requires as part of its production process. This is ballooning. And so is the use of data in the rest of the economy, both for entertainment purposes and for production processes. And we've only seen the tip of the iceberg, because there is going to be a lot of machine-to-machine communication and a lot of new ways of using data as part of the ongoing digital transformation of various production processes. What we know now is that the majority of data demand comes from about allowing resilient, fast, cheap transport of data between data centers, because ultimately this is the heart of the internet, and all of our incredibly smart devices are smart because they work in tandem with the hard lifting, the humble behind the scenes hero work that takes place in data centers all over the world for a variety of applications. And therefore, this is quite important to think about when thinking about how to design the infrastructure, the bridges, so to speak, that need to carry that data. Several of you will be quite familiar with the various topologies of the internet architecture, and also the role of NRENs as research education networks in using their own dedicated and broader connectivity infrastructures, which they share and they lease in a variety of ways and build in a variety of ways, so to make sure that economic activity can take place, which involves data transfer, just as in any other sector of the economy. And we do see that there's a lot of effort and there is funding going on for the more domestic, national level connectivity, and also the building of intra-European networks, because this is also what member states, countries are good at, building infrastructures. This is also what the European Union is good at, co-funding and making sure that there are those intra-EU networks. Then, of course, the European Union institutions themselves don't go and dig up anything or build anything on their own, but they are an important player to stimulate the ecosystem across Europe. But what about bridges to the rest of the world? That's actually a key component. It's often forgotten, and doing this humble, powerful work quietly under the seabed, hopefully undisturbed. That's what we're talking about here. That's the subsea cables don't show up in front of people's roads, don't speak for themselves, and you who are key advanced users in the research and education network know their importance. Therefore, Europe needs a substantial expansion in its internal capacity and the intercontinental submarine network in order to obtain greater centrality. And with that centrality comes the strategic autonomy, the resilience, the digital autonomy, independence that allows from a dense network of bridges, so to speak. It's not a win-lose game. It's about positioning Europe in a way that allows its maximum economic potential and the greatest research potential for the research and education networks, first of all, but ultimately about the economy. Here are some predictions on Europe, Asia, and Europe, North America. Of course, they are quite important in order to sense test that there is a business case for what we're talking about here. We know that due to commercial reasons, not necessarily research reasons, but also the so-called flap, the core of the data center and digital connectivity in the European continent is around this magic square. And that's one part of the story. And this still continues to be a powerhouse of economic benefits and will continue to be so. But what we're talking today is about thinking about a broader way to connect Europe with the rest of the world, because as mentioned today, we have connectivity for the flap and for Europe that goes through Russia, that goes through the Suez Canal, and then also submarine cables in the Atlantic. And the questions, of course, that this raises is about stability. It's about the expensiveness of those two first types of connections. It's about reliability. And when we look at other forms of infrastructure, every business and general newspaper headlines in 2021 were covered for a month about something unexpected due to the wind, the ever-given container ship, which decides to steer the wrong way, and off you go with the global trade in everything getting stuck for 30 days and more until it is fixed. Nothing malicious there, as far as we know. It's the wind blowing, and yet when you have dependency on a bottleneck, everyone loses the strategic autonomy that comes with the ability to trade with distant nations to power the economy. So that's just one example. I think it put a lot of things on people's mind, and it makes us aware of the advantages of resilience, of redundancy for the purpose of the resilience. The question of power to data centers is related to how the business case for and policy case for a polar connection helps support the future developments that underpin the internet. The intuition of this is about the capacity to expand renewable sources, wind power in particular, at large scale and lower cost. And this is where the north of Europe has a competitive advantage due to geography. Of course, it's not the only area where this is possible. And of course, the energy transformation in Europe and our autonomy in Europe as a whole depends on becoming better all over Europe at this. But clearly, there is a know-how and there is a capability to expand at scale in Northern Europe, which is delivering synergies to the possibility to deploy data centers. So we know that the levelized cost of energy is quite low in Northern Europe. Why does this matter when we think about what enhanced digital infrastructures that complement and make use of the cross-Arctic cables we're discussing today makes sense? This is because the economic intuition here is that moving bits is cheaper than moving gigawatts. So the cost of transporting data will be lower. We know it is lower than the cost of transporting energy to perform computation in data centers that are in locations where it's more expensive to get the renewable energy that is needed. So here we've done 3 stylized models in order to test and demonstrate the advantages of a solution where you have all in the Nordic region compared to all in Central Europe. Does it mean that there should be no data centers or no connectivity going to Central Europe? No, not at all. There is already abundant connectivity and more and data center infrastructures, and more of that is coming. And there are already EU policies that support this. Nothing wrong with that. But the question is one of also economic sustainability and efficiency in thinking about where is the largest competitive advantage. And this comes, for example, here in the solution with all in Nordic region, when you factor in the electricity cost, the electricity transmission cost, the data cable cost, and the data center investment cost, all of this on an annualized basis. So this is what's driving the interest and what should be driving also the business case for powering further the connectivity that lands in the Nordic region. So we've looked in our study at the broader set of economic benefits that come before we turn to the overall quantification that comes from a submarine cable capacity being significantly enhanced and built in the Nordic region, connecting Europe to Asia and the west coast of North America. So we know that there will be, of course, increase in submarine cable capacity, and then there is again, a triangle of drivers of performance benefits: decrease in latency, improved bandwidth, and route diversity. So these are all coming with a greater capacity and the specific virtuous nature of the connections. Technically challenging, yet feasible to do, and yet a significant shortcut compared to what we have to do. So this is also powering the business case, because it will mean that there will be incentives for also commercial traffic to use these routes wherever available. So that's an important. It's not a long and winding motorway that is being built here, or a bridge that will take long to cross, but it will be something that will also be a shortcut. So that also is important when we think about the order of priority of routing and is there a risk as a policymaker whenever a bridge is being built and people are advocating for it? Is there a risk that we're building so-called cathedral in the desert? Is there something that will be an empty motorway that nobody wants to pay to drive on? And this is also something what we need to evaluate. And these are factors that help us think that the risk is low. There will be consumer welfare increases also related to the rural areas in the Nordic countries, which will benefit at the margin from the more enhanced connectivity. And of course, Svalbard has been mentioned here, probably will become one of the best connected places on the planet. So if you want to take lots of selfies and in Svalbard, that will be you can do it. here's our quantification in 2 scenarios. This is the overall impact, annual GDP impact. This is a levelized GDP impact based on long-term effects of 1.4 euro billion per year in the scenario A with 1 Arctic cable, and 2.9 euro billion per year with 2 Arctic cables and connection to Europe. These economic effects require the infrastructure to be in use. There is no magic wand here. Building a bridge that stays empty doesn't deliver economic benefit beyond the capex boost to the economy of getting it built. But these are the benefits that come with a full utilization based on the existing economic models, our calibration, what has already been established in the literature. And we think they are quite powerful estimates because they do support not just the policy case, but the business case that goes above and beyond the NREN applications and bring the rest of the economy benefits with it, which ultimately is the key synergy that I think you all in this room want to unlock when putting the best case forward for policymakers to consider. There are, of course, a variety of costs and risks that need to be analyzed, and it's important to put them out there because they are part of a policy case, and no one wants a Pollyanna-ish type over-optimistic case. There are costs, weather and climate, political roadblocks. Here we've been maybe relatively conservative, where some of the tougher political roadblocks is negotiation with fishermen unions, but the world is more complex from the moment we started designing the study. There is, of course, a demand risk, and there needs to be commercial thinking to manage and minimize this. There is a chicken and egg problem, of course, of getting it built. When you think about the building we're in here, Nordic House, you enter the building, there are 20, 30 different logos on it, different tenants that are in it. But somebody had to take the initiative here, get the Nordic House in place, get the first leases, and then find others that wanted to come in. And then you have a variety of stakeholders, including Alentejo region from Portugal and so on and so forth. It takes time, probably decades, to build it and fully utilize it. So there is an important entrepreneurial activity to be done here to make it happen. And ultimately, then there is there are the broader economic benefits. Clearly, the role of research and education networks can be pivotal as an anchor tenant. Doesn't mean someone who has to take the entire commercial risk, probably not. But it's about providing a stability that significantly de-risks and shows a commitment from the public sector into this type of investment activity. Ultimately, to leverage commercial funding and the commercial engagement by reducing the risk from demand uncertainty and being advanced users, research and education network. It's an important signal. I think the video is stopped now. But I'm happy to conclude and say thank you for your time. Looking forward to the questions later on in Q&A, and looking forward to the next speaker. Thank you.
There you go. Thank you. Okay, so then I should present our next speaker, which is Professor Katarina Gårdfeldt. She's from the Director General of the Swedish Polar Research Secretariat. And for those who doesn't know it, and I think it's already been mentioned here several times, but the Swedish Polar Research Secretariat has, together with the Swedish Maritime Administration, had regular research expeditions with icebreaker Odin in the polar region. And I think we can hear a bit more about that here now, but in different context. So she will present the viability of crossing the North Pole with submarine cables. So I give the word to you.
Thank you, Eleanor, and thank you all for letting me having the word here today. Yes, my strategy here today is to present who we are, the Swedish Polar Research Secretariat, what we have done with relevance for this next moon landing mission, the Polar Connect, and then talk a bit about the strategy that we have come up with so far to make a successful cable mission. So the Swedish Polar Research Secretariat, we are a governmental agency under the Swedish Government of Research and Education. And this is our mission. I will not go into the details, you will have the slide later. But what we do in short context is logistical support and also support to a minor extent to individual researchers who are doing polar science. We do logistic planning and permitting issues in polar science, administrative support, safety training, and we also are lending equipment and clothing and transport and communications and solutions in field in order to make successful polar research expeditions in both Arctic and Antarctica. So this is the regions where we are active, Arctic, we in the Arctic, we have the Swedish Polar Research Station Abisko, and we charter the icebreaker Oden from the Swedish Maritime Agency. In Antarctica, we have 2 stations, and we also operate in the Swedish mountain areas. So partnerships is very important for us because we are a small agency. We are only 30 people, but we work with other. Collaboration is our method. And the EU is, of course, a very important partner for us. The infrastructure, I mentioned Abisko Research Station in the Swedish Arctic, Vasa and Svea on Antarctica, and the icebreaker Oden. And I will talk more about the icebreaker Oden now. She's one of the world's most powerful icebreaker. She got 4 engines, 24,000 horsepower. And she's owned by the Swedish Maritime Administration and doing icebreaker in the Baltic during the winter season. During the summers, we can charter her for expeditions. So in the year of 1991, Oden was the first non-nuclear powered research vessel to reach the North Pole together with the German polar research vessel Polarstern. And we have conducted almost yearly research expeditions with the Oden. We have been to the North Pole 10 times. And we have also done expeditions with the Oden on Antarctica together with US National Science Foundation. In this very moment, the Oden is at Longyearbyen waiting for the scientists that will get on board on Sunday. And then Oden is heading for a position North Svalbard, where she will be frozen in until the meteorologists that we have as onshore partners will direct Oden to a position where warm air is coming into the Arctic and starting the melting season this very spring. The spring season is very understudied in the Arctic. So with this expedition, we hope to know more about how the melting of the sea ice is initiated during the very short Arctic spring. So I wish them all success for this expedition right now. Next summer, we will go to a place North Greenland. It's a very complicated place to be in because it's very heavy ice in this area. We have done 2 research expeditions in the fjords there before, the Ryder expedition and the Peterman expedition, and in 2024 we will repeat this. The focus of this is to understanding the dynamic history of the impact of the marine cryosphere and the future climate change, and also implications for marine and terrestrial ecosystem in the northern Greenland and Arctic Ocean. And the focus is also investigating how the ice sheet in the northern Greenland can contribute to global sea level rise. And in this expedition 2024, we are so happy to collaborate with the Norwegian icebreaker Kronprins Haakon, who will also join this mission in 2024. So now I'm moving over to strategic planning and multi-vessel approach. The Central Arctic Ocean is a very complicated place to operate in. It is heavy ice, and the ice is quite unpredictably now when the climate change is changing the circumstances for the ice coverage. Therefore, we have applied a method that we call strategic planning with a multi-vessel approach. And I will give you 2 examples of that. The first one was conducted in 2004 when we made the Arctic Ocean Coring Expedition, the ASEX, successfully. And the next one was planned for 2022. It was the planning of the Arctic Ocean Paleoceanography, ARCOP. Unfortunately, this was postponed because it was planned just when the Russian invasion of Ukraine started, and there was a lot of security issues. So this is postponed to a later period. When you do the multi-vessel approach, you must know which mission you have on the expedition. And therefore, you must think about the different regime of the Central Arctic Ocean. We have the very Central Arctic Ocean with a dense pack ice year round. And we have marginal ice zone with broken up ice, and we have areas with first year ice and landfast ice. And depending on where you want to go, you must strategically select the icebreaker that you want to assist the research. We have icebreakers, that is vessels that are constructed to protect and assist other vessels in the ice. And the vessels are built for very aggressive operation in ice. For example, the icebreaker Odin and the polar research vessel Polarstein. And we have ice-breaking vessels, that is vessels that for its own progress may operate aggressively in ice. And there are examples of this, for example, research vessel Academic Fedorov, Sikuliak, and Agulas, and so on. And then we have ice-classed vessels, vessels that are ice-strengthened and may follow icebreakers and even proceed on their own in lighter ice conditions. And it's very important to select the right vessel for the right operation. The complication here is that different nations has different classification system for icebreaker. So if you talk about an icebreaker and so this is polar class this and this, you don't really know what it is. Therefore, for the report that we made for the European Commission project ARISE, we made a comparison with different classification systems and put them in parallel so that you can compare and select the right vessel for the right operation. And as you can see here, there is only one vessel that is Polar Class 2+, and that is the icebreaker Odin. Then we have strong vessels like Kronprins Haakon, Polarstern, and Amundsen, which is between PC3 and PC2. And then we have a lot of vessels that are PC3 or below. So this is important for international collaboration to select the right vessel and make this puzzle. So what we have done for the Arctic Ocean Coring Expedition 2004, which aimed to bring up sediment cores from the North Pole or the area around the North Pole in order to use the sediments as a library for the Earth's climate history. We put 3 ships together. It was the Swedish Vidar Viking, and the Swedish Odin, and the Russian icebreaker Soyuz. And this is a picture from above where we can see that the coring ship here is at the position for the coring site. And then we have the icebreaker Odin to keep the site clean from small ice flows. And then we have the strong icebreaker for the far ice management, breaking the big ice flow. So this is a system with a strong icebreaker, a weaker icebreaker to protect the coring ship. And this was very successful. The scientific impact was huge from this expedition. It was very many countries involved, and it was yes, 5 minutes. And this is some results from this complicated moon landing expedition. From 421 meter sediments, we can say a lot about the climate history on Earth. The ARCOP was the next mission. The same, we made a setup with a multi-vessel setup. And this was the A6, the first. This we planned for ARCOP, which is postponed. But from this presentation, I would like to just show that we know the area quite well, and we know what it takes in terms of different ships and the strength of different ships. So we have here an ambition, and that is to build a new research icebreaker, a PC1 class. That will be the first on Earth, because if we don't count on the nuclear-powered icebreakers that Russia has, but this will be the first one for Europe. And our ambition is that it will be a multi-purpose, climate-neutral icebreaker for science and polar logistic. It will be climate neutral. we are looking at the propulsion from e-methanol, which can be produced from biogenic and renewable sources, and also in combination with hybrid propulsion and power. It will be no soot, minimum carbon footprint, and so on. And for the Polar Connect, again, we will apply a multi-vessel approach in the Central Arctic Ocean. First, icebreaker Odin will continue to map the seabed in the Central Arctic Ocean prior the cable laying operation to locate optimal positioning of the cable path. Then an ice-strengthened cable vessel will be supported with far and near ice management, as I showed on the other operations that we have made, by two strong Swedish icebreakers, PC1 and the PC2 Plus, that is Odin, respectively. And the estimated time for the cable vessel in heavy ice will be 30 plus days in 2-3 knots, which is normal for a cable laying vessel. We will have a system for connections and maintenance, and also a plan for remediation of the seafloor. A full technical report will be delivered by us to VR Sunet and Nordic in September 2003. And finally, I will say that international collaboration is our method at the Swedish Polar Research Secretariat. And Korea and Japan will be important partners for us in this project, and we welcome the early engagement that we have seen from South Korea Kopri, for example, and we also appreciate the very close collaboration we have had with both Jamstek and Kopri for polar research, both in Antarctica and Arctic. Thank you. I hope I kept my time. Yeah.
Thank you very much.
Thank you.
Thank you very much there. Okay, so now it's time for sort of a more research-oriented part. So I will present, welcome to the stage Professor Stein Stanven from Nansen Environment and Remote Sensing Center in Norway, who will present the need for scientific observation in the Arctic. So, here we go.
Thank you. First, a few words about myself. I am an oceanographer of training. I have been working in the Arctic for many years, collecting data and looking into the problems and challenges you have when you want to be in the Arctic and collect data. So today I will talk a little bit about our ongoing work and why we need data, and also how we can improve this if we are able to use a cable network. I am speaking here on behalf of my colleague, Hannes Hagen, who is driving several of our projects now. And one of the things we are interested in is the ocean. What happens in the deep ocean of the Arctic? And we have this current map here showing how the warm water from the south travels to the north and heating up the internal Arctic Ocean and can contribute to melting of the sea ice. We don't know exactly how much it is doing it, but if look at this figure, the ocean has different layers. We have the so-called Atlantic layer here between 300 and 700 meters, which is the warm layer. On top, we have colder layers, and we have ice on the top. So the question is, what happens if we have more warming here, and this warm water come up to the surface? It will enhance the melting. And this is partly going on today, but we don't know really how this process is working. So we want to know this better. To do that, we have just finished one experiment, which is about measuring temperature by acoustic waves. So we have transmitted acoustic signals across the whole Arctic Ocean, from north of Svalbard over to the north coast of Alaska. This experiment, called KTEX, was conducted over a period of 1 year. And when we did this, we had to have people working in the ice, making holes in the ice, deploy instruments under the ice, and then recover the instruments under the ice again after 1 year. Example of these data we can see here. The acoustic data travels quite fast. A signal travels about 1.5 kilometer per second. So it means that if you send an acoustic signal from across the whole basin, it takes about 30 minutes or 1800 seconds. And we have received the signals at different depths. And all these signals here, we can calculate exactly how long time it takes to travel. And since travel time is a function of temperature and also pressure and salinity, we can estimate the average temperature over this distance. We also have to compare the acoustic measurements with traditional profiles, oceanographical profiles, where we look at temperature in different places obtained with instruments. We see here temperature profile from about 50 meters down to 1,000 meters in 3 different places. And to the right, we have the same profiles taken from climate models. And we all know that climate models is the main method we have to predict what will happen with the climate in the coming years. And we need to be sure how good are these models and can we improve them? And we see that all those profiles there comes from different models. They have a different performance and everybody's interested to improve the quality of the models. So what can we do with cables? These are figures we have borrowed from Bruce Hove, who has been involved in this project, which is a joint task force between ITU, WMO, and UNESCO IOC. And the question is, can we use cables? Because we have many other observing methods for the ocean, which is fine, but in the Arctic with sea ice, it's not so easy to use the methods that we can use in other places. However, if we can have instruments under the ice, on the seafloor, we can sort of avoid the ice problem. Well, to some extent. So we have the smart subsea cable systems. And these are slides I borrowed from Bruce Hove, and he had discussed many of the things we have talking about today. There are already many subsea cables. Question is, how can we connect research instruments to them? Is that feasible? How can we do it? And there is a lot of ongoing efforts around the world. This is an example from Portugal, where they are trying now to install a cable already next year. And we are following this development to see how we can benefit from this in the Arctic. And when we saw this plan for this cable, which goes around Greenland through the Northeast Passage and over to Japan, we were thinking, how could we, as ocean researchers, connect to that system? And ideally, we have, as I will show in another slide, we are planning some deployments of moorings in the Eurasian basin. And we have colleagues in the US who are planning similar deployments in the Beaufort Sea. And if we could connect to such a cable system, we would have immediately access to the data in real time, and we could have many other things beneficial for the science if this was doable. A few words about this new project called HIAOS, High Arctic Ocean Observing System. We will next year deploy more deep sea moorings in the Central Arctic Ocean with acoustic sources and receivers. The sources will transmit signal which propagates over the whole ocean. We will also have receivers on each mooring. They will receive the signal so we can calculate travel time and we can estimate temperature. But we can also use the signal to navigate under ice platform like floats, as we see in this case. So there are different applications for this system, as we have mentioned here. We can also detect marine mammals, we can detect geohazards, and we can measure human-generated noise. So the plan is, this is planned for the next 3-4 years, to deploy these moorings in the Eurasian basin. And of course, it is just data which can only be collected after we have recovered, hopefully successfully recover these instruments which is planned in 2026. So the vision is, if we had our system connected to a cable system like this one, a trans-Arctic smart cable, as we hear about today, we will have a perfect possibility to collect much more data using the benefit of that cable. And here indicated with all these green points here, you could have sensors along the cable. But more importantly, we need not only on the seafloor, but we need these moorings which collects data in the water column from bottom to surface. These moorings should be connected to the cable so that we get data from the whole water column transmitted through the cable. So that's our vision for the future. And just a few remarks at the end here. 4 main requirements. We need to have national international collaboration. We need robust observing platforms and sensors. So we need to collaborate with a technology provider who already works subsea and offshore industry. Operationalization of the data delivery chain, because there will be a lot of data, so we need to be able to handle the data in an efficient way. And sustainability of the observing system, that of course comes with funding. So I don't need to say more about that. I hope this was okay. Thank you. I guess I've used my time. Thank you very much.
Okay, and now it's and now it's time for Martin Landra from the Norwegian University of Science and Technology in Norway, and he will explain how research using North Pole fiber infrastructure can be conducted. Actually, so
thank you. So I'm leading a Center for Geophysical Forecasting in Trondheim, Norway, and we are using fibers as listening equipment for sensing. So that's what I'm going to talk about. And one of our partners in this center is Yamstek in Yokohama in Japan. Okay, thank you. So these are the fibers that we have been using in our research. It's connecting Longyearbyen. We are now at Svalbard, connecting Longyearbyen to Ny-Ålesund. These 2 fibers were deployed in 2015, and we are using them for sensing. They are 250 kilometers long, and these fibers are being used in one EU project, Submerse, and also in an upcoming one called Sea Sounds. So, in 2020, we did a first test where we sensed using an interrogator that sends light into a fiber. And then when an acoustic wave or signal hits the fiber, the small particles in the fiber are moving a bit, and that we can measure and transform it back to a sound signal. So what we did, this black line here is the fiber at the seabed. The red line is a cargo vessel sailing across the fiber. The water depth is here 300 meters. So it's in Isfjorden at Svalbard. And the white dots, that's the interesting thing here. That's our estimation of the position of the ship, pretending that we don't know the answer. So this means that if this has been a ship without AIS on, we could still see it. We see it approximately 1 kilometer before it hits the fiber and 1 kilometer after. And we can determine the positions as accurate as this. We can even see what we call the Doppler effect. That is similar to when an ambulance, we heard an ambulance here today. When the ambulance is coming towards you and when it's pausing, the frequency changes a bit. You have probably noticed that. It's called the Doppler effect. And we see that for this ship, even though the ship, and then we can, when we measure this change in frequency, we can estimate the velocity of the ship, 11 knots. So we can find out a lot of things here. What is more impressive is that we saw a lot of blue whales in this test. So these are blue whale calls, distance in kilometers, and seconds along this horizontal axis. So these are blue whale calls, and there are two whales communicating here. This is whale number 2, and this is whale number 1. And what we can do is to sum these signals and create the sound file, how the whale vocalizes. So, and that is quite fantastic. We use a fiber that is digged 2 meters below sea bed, and we can create the sound of a blue whale. So we can listen to it and recognize that, yes, this is a blue whale. So that's, when we discovered that, that was a kind of a great discovery for us. And we got a lot of media attention. Stein, Newsweek, more than 100 news channels were interested in this. We can even use the blue whale as a seismic source to map the subsurface. So what we see here is the direct arrival from the blue whale, and then we see the first reflection, which indicate that we can see 100, 200 meters below seabed. And this is at 25 kilometers. Further out in the East Fjorden, we see that this layer has been thinning. So it means that the blue whale can actually map the subsurface. Quite fantastic. In 2022, we did a new test using both of these cables. And this is a recording of an earthquake that happened south of Spitsbergen. And we see this is the P wave, which is the fastest wave for all earthquakes. And this is the shear wave that you see here. And this is 256 kilometers. And we are using now 2 interrogators that send fiber optic light into the fiber from both sides. And then we see that in the middle, approximately here, the signal to noise ratio is lower. So that the earthquake signal is kind of drawing in the background noise. And that is because the longer in the fiber we emit the signal, the more attenuation we get. So that was a good test. The method is working. So we can use this communication fiber for sensing. No problem. 6th of February, this is the fiber outside New Ålesund. We measured the earthquake in Turkey that we all know about. It's clearly visible, the first arrival here along the fiber. These are specific traces where we observe this as normal earthquake data. This can be compared to normal seismological data. Then we did one step forward. We exploited the 2 fibers to estimate the position of fin whales. This is a fin whale that you see here. What we see here is approximately 20 kilometers of data. And again, these signals that are recorded by this fiber. And we see here 24 calls. So the fin whale has been very active here. And since we can observe it on both cables, that are separated by 2-3 kilometers maybe, we can determine where the whale is when it's vocalizing. So this is a paper that was published last week, actually. So we are quite proud of this picture, because what we have done here is to, if you look at the bar here, it's 5 hours period. So we have been analyzing our data, some 50 terabytes maybe of data, over a 5 hours period. And we have detected, I think it's 7 whales there. These 7 whales are maneuvering or swimming in this area, which is some 30-40 kilometers long for this period. And we can monitor them. So if you look at this guy, or female, I don't know, started to vocalize 1.5 hour after we started the recording here. And it went south, then east, and turned around. The other whale over here starts here and goes directly to the west. This guy is a lazy one. And we can estimate the velocity, the speed of each whale, and the direction So this is quite fantastic. We can track whales as a function of time using these two fibers. We can find out how they communicate, we can find out the type of the whale, and we can use this for biological mapping. So I think it's the first time. Then we have one slide on oceanography. This is the low frequency part of the fiber that we can measure. So these are distant storms. This was discovered by Walter Monk, which is quite famous, Austrian oceanographer. He derived this simple formula that if you have a storm at a given distance x, then you can estimate the distance to the storm if you measure the slope of this signal created by that ocean storm. You see that all of these signals, they are monotonically increasing versus time. This is a period of 14 days we have recorded, and we're using very low frequency data, below 1 Hertz. So you cannot hear these signals with your ear, but you can measure them. So if you take, for instance, the first one here, we can look up into meteorological data, and we find out that this was the storm called Edward. It's 4,100 kilometers away, and that fits very nicely with this slope that we're using here to estimate it. The second storm is further away, takes more time, you see, lower slope. That's a storm offshore Brazil, 13,000 kilometers away. So we can sit in Svalbard and listen to storms a very long distance away. So that's another possibility. This is also coupled to some lunar research that I'm involved in, because we plan to use these dust fibers on the moon. So that's the next step, to measure gravitational waves. Then we have another activity where we look deep into the Earth. This is close to the mid-Atlantic ridge, which you have to cross with this fiber. You have to pass the ridge somewhere. And this is at what is called the Mons Ridge, where we see shallow, by using electromagnetic data, we can map the flow circulation. That creates this black smokers that you see here. Here, metals are actually being deposited naturally at the seabed. So it's a lot of activity there. But we are most interested in the deep, in mapping the melt. So here we see that the melt is very asymmetric. This is 100 kilometers deep. And we see how the melt is kind of feeding into that mid-Atlantic ridge. We want to understand how this melt is looking like all over the mid-Atlantic ridge. So we're doing several surveys, trying to understand how this melt is moving. And of course, the sensational thing here is the asymmetric thing here. We used to think that it was symmetric below the ridge. So this is a map of the ridge, and this is the map you have shown several times. We are doing research here, and of course, if we can do research along a path like that, that would be fantastic. It's whales, it's earthquakes, deep imaging of the Earth. There are a lot of things we want to use this for. Now we have been focusing here. We have done surveys here and here and here, and of course at Svalbard. But of course, if we have a fiber that goes all the way, we can do a lot of research on marine mammals, but also on deep Earth imaging. So that's what is our hope, that we can get something like this. And what we have discussed, me and Olaf, is to make it take a branch out. If the white line here is the fiber we are talking about, then we would like to have some branch outs to cross this fantastic terrain that we have at the ridge. So I think that's, yeah. I think I'd sum up. So to use these fibers at the seafloor, we think it's an efficient tool for tracking whales. We need to develop efficient and fast algorithms. We are going to digest like terabytes of data every day. We think it's a potential tool to avoid what we call ship strikes, when ships runs into whales without noticing, especially big ships, they don't notice. And we think that a lot of whales are killed this, or we know that. So that's interesting. Oceanography I have measured, seismological studies, earthquakes, we have gas flares, explosions, things like that are easy to detect and monitor by these fibers. The present range of DAS is 100 to 150 kilometers, but we think that within a couple of years, we will have amplifiers similar to the one we have for communication cables at the same distance, because the magic number here is 100 kilometers. So if we can have amplifiers for DAS every 100 kilometer, we are in business. So that's what we I'm pretty sure that we will see that within some years. And it's also, I think we can say today, it's possible to do both telecommunication and DAS sensing in the same cable, in the same fiber. So we are there today. So that's already in place, I would say. So then I think I stop there. Okay.
Thank you very much, everyone. Okay, so now we will actually go to the Q&A session. And with that, I would like to thank all of you who have participated online. The streaming will now end, so I think we're going to close that off. And we'll only continue with all of you who are here today. For those who participated online, I hope you enjoyed this seminar, of course, and bye.